Alright everyone, and welcome back to the AI Research Roundup. I'm your host, Alex. Today, we're looking at SuperEdit, Rectifying and Facilitating Supervision for Instruction-Based Image Editing, published May 5th, 2025. This paper tackles noisy supervision signals in AI image editing. That's when text prompts and example image edits don't quite align, confusing the AI. SuperEdit's core idea is to create better editing instructions, rather than relying on complex methods like pre-training or additional vision language models, which are AIs that understand both images and text. They achieve this by rectifying instructions and using, quote, contrastive editing instructions, essentially showing the AI both good and bad examples for an edit. And for those interested in diving deeper into how this works, the authors have also made their code available. On their GitHub repository for SuperEdit, you'll find the official implementation, including scripts for setting up your environment, running training and evaluation, and even a Gradio demo, which is a neat tool that lets you easily create a web interface to try out the AI model yourself. This repository is a great resource if you want to see SuperEdit in action. Alright, so to really see what SuperEdit can do, Figure 1 offers some great insights. Panel A displays several example edits, from changing entire backgrounds, like making a field snowy, to adding small details such as a pink tie to a boy. Then, Panel B graphically compares SuperEdit with other AI models. This shows SuperEdit getting a higher overall score on the real edit benchmark, while using much less training data and a significantly smaller model. It has about 1.1 billion parameters, which are the internal adjustable settings an AI learns, versus over 14 billion for a competitor. Finally, Panel C shows human evaluators also preferred SuperEdit's results, reinforcing its effectiveness. So building on those impressive results, Figure 2 now shows us the different system designs or architectures. Panels A, B, and C illustrate how other methods handle those noisy instructions we discussed. They typically use a variational autoencoder, or VAE, which helps the AI learn and reconstruct images, and CLIP, an AI that links images with text descriptions. This information, along with the noisy instruction, then goes into a UNet, a common AI network often pre-trained for text-to-image tasks. Panel D, SuperEdit's approach, uses similar components but crucially starts with a, quote, rectified instruction, focusing on better input quality from the get-go. Okay, so Figure 2 showed us the what of SuperEdit's architecture. Now, Figure 4 gives us a peek into the how, specifically how the model handles different types of edits over time. We see examples like changing a background to a cloudy sky, turning a statue into a cyborg, or transforming it into a watercolor style. The figure illustrates that these edits happen in stages. Early on, the model makes global changes, like the overall scene. Mid-stage, it focuses on local attributes, and then late stage, it refines the details. Style changes, interestingly, seem to happen throughout all stages. This understanding of, quote, diffusion generation priors, or how AI models build up images step by step, is crucial for SuperEdit's ability to rectify instructions. Alright, so we've talked about how SuperEdit understands the stages of image generation, those diffusion generation priors. Figure 3 now directly contrasts SuperEdit's approach for creating editing instructions with existing methods. Panel A shows a typical pipeline where a large language model, an AI, trained on vast amounts of text, generates an instruction. Then, diffusion models, AIs that create images by gradually refining noise, try to apply this instruction but often make mistakes, like changing the background incorrectly. Panel B, SuperEdit's way, uses a vision language model to analyze both the original and the edited image, applying those diffusion priors we just discussed to create a much more accurate, rectified instruction. Okay, so we've just seen how SuperEdit uses a vision language model and those diffusion generation priors to create much more accurate, rectified instructions. Figure 5 now shows us how the system takes this a step further by creating, quote, contrastive instructions and using them in training. Panel A illustrates this first part, where the vision language model, starting with the original image and that good rectified instruction, like add a pair of black sunglasses for the dog, intentionally creates wrong instructions. For instance, it might change the color to purple sunglasses or the object to earmuffs. Then Panel B shows the training pipeline. The AI model is fed both the correct, rectified instruction and one of these wrong instructions. The goal is to train the model using what's known as a triplet loss, which is a learning method that encourages the model's prediction for the correct instruction to be very similar to the actual desired edit, while making its prediction for the wrong instruction very different. This helps the model really fine-tune its understanding of subtle differences in instructions. Alright, so after seeing how SuperEdit fine-tunes its understanding with those contrastive instructions and the triplet loss, Figure 6 really brings it home with a visual bake-off. We're looking at several editing tasks here, like replace the tiger with a lion, or add a pink tie for the boy. Each column shows the original image, the instruction, and then results from a bunch of different methods, with SuperEdit's attempt right at the bottom. And generally, SuperEdit's edits look more on point. The figure also includes scores for following. That's how well the edit matches the instruction. Preserving, how well it keeps the parts of the image it wasn't supposed to change. And quality, the overall visual appeal. SuperEdit consistently scores well across these. Now, Table 1 gives us the hard numbers from the Real Edit benchmark, which is a standard test for these kinds of models. It compares SuperEdit to a bunch of other methods. We see those same metrics we just talked about, following, preserving, and quality, plus an overall score. And SuperEdit, our method, is at the bottom row, consistently achieving the highest scores. For instance, its overall score is 3.91, beating SmartEdit's 3.59. What's really impressive is that SuperEdit does this using only 40,000 training images, way less than others, and with a smaller model size too. As those numbers in Table 1 clearly show, SuperEdit really packs a punch, outperforming other methods even with less training data. The key here seems to be its clever way of learning from both perfect and slightly imperfect instructions, making it much sharper at understanding exactly what we mean. This work is a significant step towards more intuitive and reliable image editing using just our words. Thanks for tuning into the AI Research Roundup. I'm Alex.